This is a 3D printed ventilator. I created it in response to the MHRA's request for a rapidly manufactured ventilator system. This is only a prototype. It's not intended for use on humans. A system like this needs a lot more development and testing before it's safe. I have not used this on myself, and I don't plan to use this on myself because I'm not a medical professional. Also, forced ventilation is dangerous. Don't do it on your own. So here's a close-up of the system and how it's built. I'm using mostly 3D printer parts. I just built a Prusa printer, so these were in mind. For this demonstration, since the motor isn't running, I put a idler pulley on the motor shaft, and this here is just holding the pulley on. We have a GT2 belt. It runs through two idler pulleys here and here. It connects to the top of the pulley system here with a tensioning system for the belt, and then extends down into to connect to the piston down at the bottom. These are 8mm guide rails with the 8mm bushings. For the bellows of this system, which you can kind of see on the inside of it, and you can see them sort of in action as this thing moves, I used 4-inch vacuum hose, the type you would use for dust collection systems. This has a lot of compressibility in this direction, and it's got metal wires on the inside of it to support against a negative pressure. So that's very important for this type of system. That is held into this system with some 3D printed band clamps, but you could also use the 4-inch tube clamps as well. This port right here is the inlet port. It could have just been a hole to pull air in. I put the same style ports we're using over here so that if they needed to hook oxygen up to it or some oxygen air mixture, they could. As the piston inside of here moves upward, it draws gas in through this port, and just on the inside there's a check valve that prevents gas from coming back out after it's been pulled into the system, or at least coming out of that hole. When the piston then compresses the gas moves through here into this relief valve. Inside of this relief valve there's another check valve. This thing comes apart. So this is the check valve. It's the same style check valve as used on the inlet. The gas pushes the rubber up as it flows from in the tank to the expiration tube. If the pressure inside of the expiration tube exceeds the set pressure of this relief, then the relief poppet lifts up and allows the gas to vent. And this has a similar silicone gasket underneath it to help it seal against the top of this relief cavity. So gas flows down this tube into the inspiration tube. When the inspiration phase is complete, the pump will start moving up to intake air. That also lowers the pressure inside of here to below atmospheric pressure. There's a valve just on the inside of the tank connected to this port. So as the pressure in this tank falls, the valve opens, allowing flow of gas into this port and out of this port over here. And this is not a relief valve, but a back pressure valve, because all the gas that goes through the system has to lift this up to escape the system. The inspiration and expiration tubes are connected to these ports and connect to our lung simulator. The lung simulator has a similar bellows style piston on the inside of it, and that is simply connected to a mass. So as we push air into this system, this mass gets lifted up and provides some back pressure on the air. So during the expiration phase, this mass is responsible for pushing the air out of the lung simulator. This pressure sense tube goes over to my fancy pressure test setup. As gas pressure comes into this tube, it pushes liquid up this tube to give us a measure of the pressure inside of the system. Unfortunately, I didn't have any food coloring, so my pressure sensor now smells like vanilla. It's actually kind of nice. So I set this weight to put 10 centimeters water worth of back pressure onto the gas we put into our lung simulator. And this weight is set to put a 20 centimeters of water back pressure on the expiration gas that's trying to escape the system. So in this case, this weight shouldn't be able to push gas out of the system. It does fall anyway because it's a fairly leaky system. That's what happens when you 3D print things. So what you're seeing as this falls down is the leak rate, both externally out of the lung simulator and whatever leakage goes through this because it's not a perfect valve. But you'll be able to see that here. And this is the rate at which gas is leaking out of the system. Now, if I take away the weight, it'll go from 20 centimeters of water back pressure to 10 centimeters of water back pressure because this system has some weight to it as well. But you'll be able to see the difference in speed when that's removed. Now this mass is able to push gas out of this valve here to exit the system. And this here is controlling the maximum inspiration pressure. And you see I push this down fast, you can see the water pressure is getting up to roughly this level here, which is 10, 20, 30, 40, 50 centimeters of water, which is where I have this weight set. If you want it lower, you put less water in it. If you want it higher, put more water in it. But see that again, getting to the roughly 50 centimeter location. If I push down on this, which is adding weight, you'll see it'll be able to go higher. I would be able to blow water right out of it too if the system wasn't very leaky. But that's how this system works. If I remove this weight here, it won't be able to lift the mass at all because all the gas is escaping out of this valve down here. That's how it works. And here's a shot of the system running under motor power. The very first attempt to do this immediately blew out the motor controller I bought. This is the 84 ounce-inch NEMA 17 motor, and they pull a lot of amps, so you have to be careful about the motor controller you select. I'm running this off of an Arduino, a 24 volt 5 amp power supply, and this motor controller. So this is what I did during forced isolation. Well, that and enjoying this great location.